The normal distribution has an incredibly fundamental and special place in statistics. It is one of a small set of attractor distributions, a distribution that draws other distributions to it through operations on data, like sums and like averages. The normal distribution was independently described by two individuals, Carl Friedrich Gauss and Pierre-Simon Laplace. Now, Gauss was a mathematician and a scientist, and in 1809 he wrote a paper describing the normal distribution. If you ever want to feel inadequate about yourself, read about the achievements of Carl Friedrich Gauss. Before he was 19, he already had a full professorship. Before then, he had to publish papers under pseudonyms or anonymously so he didn't embarrass his advisors whose theories he had overturned with his mathematics. Pierre-Simon Laplace, no slouch himself, was an astronomer and also a mathematician. Remember, statistics and astronomy have a long history. Arthur Eddington was also an astronomer. Remember, he was the one who argued with Fisher about the estimation of the population quantity of variability. Now, what these two titans described was the normal distribution, also known as the Gaussian distribution. Now, you don't need to know this formula, but I do want you to notice something about it. It's one of a special class of exponential functions. That's because we're taking Euler's number to a power here. But in this function, we only need two specific values to draw the normal distribution. That is, we need to provide this function with a value of mu, the mean of the distribution, and a value of sigma, the standard deviation of the distribution. Everything else in this function is a constant. Pi is a constant, Euler is a constant, and x is the location on the x-axis where we're trying to describe the height. What's critical about this is the shape of the normal distribution has nothing to do with its location or its standard deviation. By providing a location and a standard deviation, we're effectively drawing the identical curve, which is why when we looked at the proportionality of an IQ distribution and of the BDI distribution, as long as we were talking about the same location in the distribution, which is what z-scoring does for us, we found identical proportionality. Let's check this out. Suppose we have a mean of 0 and a standard deviation of 1. I've entered those values into the formula, and this applied a scale to the normal distribution. If I try different values, how about a mean of 100 and a standard deviation of 15? Notice I didn't have to redraw the distribution, I simply added another row for our axis. That is, a location of 1 for that first distribution, which actually happened to be the z distribution, is really the same as a location as 115. Let's try the BDI distribution, a mean of 16 and a standard deviation of 4. Notice again, I didn't have to redraw this distribution. Instead, I just added another axis. All of these locations are, in essence, the same place on a normal distribution. So me asking the question, what proportion is beyond a z-score of 1, is the same thing as saying beyond a value of 115 on an IQ distribution or beyond a value of 20 on the BDI distribution. They're all identical. Now let's go back to that first distribution, the one that had a mean of 0 and a standard deviation of 1, because this is a rather important distribution in statistics and one we'll talk about at length. This is known as the z distribution, which is just a normal distribution with a mean of 0 and a standard deviation of 1. Remember, what's convenient about z-scores is we can bring any other distribution to have a mean of 0 and a standard deviation of 1. If the distribution we're converting starts off with a normal shape, then, after we z-score all the values, it will be this distribution. As we'll see, there are very important things in statistics that are normally distributed, so it's going to be important that we know a little bit about the proportionality of this z distribution. I'll give you some rough proportions here. Now, these proportions are approximate, but give us an idea of the area under the curve. Notice, if I bring back the scales from before, let's actually try to answer the questions I posed earlier, specifically the proportion of an IQ distribution greater than 115, or the proportion of a BDI distribution greater than 20. Notice these are the exact same locations as a z distribution at 1, and if we add up the rough proportions, 0.14 plus 0.02, we get the value we found before, around 0.16. Remember I said we didn't actually have to open a data table and count up the number of observations? This is what I meant. We know the proportions of a normal distribution, So if you can convert a question to be a question about a z-score, and you know that the distribution is normally distributed, you can answer the question directly. Now, importantly for us, there's one very special thing in statistics that, under a wide range of conditions, will be normally distributed, and that is sampling error. Remember, sampling error is the error that exists between our sample statistics and our population parameters. And again, under a wide range of conditions, sampling error will be normally distributed. Because we know a lot about the normal distribution, we're going to be able to quantify and predict how much sampling error we should expect to get, which is going to give us the key to making inferences about populations from samples.